determine the minimum ampacity of branch circuit conductors for two individual motor circuits installed in the same conduit for two 25 horsepower 3-phase 208 volts design B motors in an area with an ambient temperature of 40 degrees Celsius using THW conductors, we must consider the full load current temperature correction and the number of conductors in a raceway. Let's begin. Firstly, find the full load current from NEC table 430.250 for a 25 horsepower, 3-phase, 208 volts motor. According to the table, the full load current is 92 amps. Secondly, apply the ambient temperature correction factor. Table 310.16 provides the ampacity correction factors based on ambient temperature. For THW conductors at 40 degrees Celsius, the correction factor is 0.82. Multiply the full load current by this factor. That is 92 amps times 0.82, which equals 75.44 amps. Thirdly, consider the number of conductors in the conduit. When multiple conductors are in the same conduit, their ampacity must be derivated according to NEC table 310.15 current. Since there are two sets of 3-phase motor circuits, there are a total of 6 current-carrying conductors in the conduit. According to the table, for 4 to 6 conductors, the derivating factor is 80% or 0.8. Apply this derivating factor to the temperature-corrected ampacity. That is 75.44 amps times 0.8, which equals 60.35 amps. Fourthly, calculate the minimum ampacity of each branch circuit conductor. For a 3-phase system, divide the adjusted ampacity by the square root of 3, approximately 1.732. This gives you 60.35 amps divided by 1.732, which is approximately 34.84 amps. Therefore, the minimum ampacity of each branch circuit conductor should be approximately 34.84 amps. To determine the minimum wire size for each branch circuit, consult table 310.16 in the NEC to find a THW conductor with an ampacity equal to or greater than 60.35 amps as calculated earlier, before derivating for the number of conductors. Because you already factored in the ambient temperature, but not for the number of conductors in the conduit, because the NEC requires that you use the table to look up the wire size before derivating for the number of conductors in the raceway. A 6 American wire gauge copper conductor with THW insulation has an ampacity of 55 amps at 40 degrees Celsius before derivating for more than 3 conductors in a raceway. An 8 American wire gauge copper conductor is not sufficient. Therefore, the minimum wire size for each branch circuit is 6 American wire gauge. Now, let's determine the demand on service conductors for the warehouse. We are given a lighting load as 10,000 volt amps. The receptacle load is calculated based on 60 receptacles. For a non-dwelling unit, each receptacle is typically calculated at 180 volt amps per receptacle, according to the NEC. Therefore, the receptacle load is 60 receptacles times 180 volt amps, which equals 10,800 volt amps. The total building load is the sum of the lighting load and the receptacle load, which is 10,000 volt amps plus 10,800 volt amps, equaling 20,800 volt amps. To calculate the demand on the service conductors, the NEC allows for demand factors to be applied to non-dwelling units. The specifics can vary based on local codes and the nature of the loads. A common approach is to apply a demand factor of 80% to the largest load and 60% to the remaining load. In this case, a lighting load is the largest load at 10,000 volt amps. The demand from lighting is 80% of 10,000 volt amps, which equals 8,000 volt amps. The remaining load is the receptacle load of 10,800 volt amps. The demand from receptacles is 60% of 10,800 volt amps, which equals 6,480 volt amps. The total demand on the surface conductors is the sum of the demand from lighting and the demand from receptacles, which is 8,000 volt amps plus 6,480 volt amps, totaling 14,480 volt amps. This is calculated by first multiplying the largest load by 0.8. In this case, the lighting load of 10,000 volt amps, and then adding to that result the remaining loads multiplied by 0.6. In this case, the receptacle load. Let's start with the receptacle load calculation first. 60 receptacles times 180 volt amps equals 10,800 volt amps. Then the calculation looks like this: demand equals 0.8 times the largest load, which is 10,000 volt amps, plus 0.6 times the remaining load, which is 10,800 volt amps. Demand equals 8,000 volt amps plus 6,480 volt amps. Demand equals 14,480 volt amps. Therefore, the demand on the service conductors for the warehouse is 14,480 volt amps. The calculation involves determining the full load current from the NEC tables, applying temperature correction factors, accounting for the number of conductors in a raceway, and then selecting an appropriate wire size based on the adjusted ampacity. For the warehouse demand calculation, it is important to consider demand factors, which may vary depending on local electrical codes and the specific nature of the loads. Consulting the relevant NEC tables, specifically Table 430.250 and Table 310.16, is crucial for accurate conductor sizing and ampacity adjustments. When dealing with multiple conductors in a raceway, NEC Table 310.15 cone provides the necessary directing factors to ensure that the conductors are not overloaded. For non-dwelling units, the calculation of demand load typically involves applying demand factors to both the lighting load and the receptacle load, as per NEC guidelines. Accurate calculation of full load current is essential because it serves as the starting point for all subsequent adjustments and calculations. The ambient temperature correction factor is critical in ensuring that conductors are not operated beyond their temperature rating, especially in environments with elevated temperatures. When multiple conductors are grouped together, the directing factor accounts for the reduced heat dissipation capacity of each conductor, preventing overheating and potential failures. In practical applications, it is important to consult local electrical codes and regulations, as they may impose additional requirements or modify the NEC guidelines. When determining the appropriate wire size, it is crucial to select a conductor with an ampacity rating that meets or exceeds the calculated minimum ampacity. Demand factors are used to account for the fact that not all loads will be operating at their maximum capacity simultaneously, allowing for a more efficient sizing of service conductors. Proper conductor sizing and demand load calculations are essential for ensuring the safety and reliability of electrical systems in both motor circuits and warehouse applications. Failure to accurately account for temperature, conductor bundling, and demand factors can lead to overheating, voltage drops, and potential electrical hazards. A thorough understanding of the NEC guidelines and local electrical codes is necessary to perform these calculations correctly. The full load current for a 25 horsepower, 3-phase 208 volts motor is found in NEC Table 430.250. The ambient temperature correction factor is found in Table 310.16. The directing factors for multiple conductors in a raceway are found in NEC Table 310.15 cone. The standard method for calculating receptacle load in a non-dwelling unit is 180 volt amps per receptacle. Demand factors allow for more efficient sizing of service conductors based on realistic load expectations. Firstly, to recap the motor circuit calculations, you have to find the full load current of the motor from Table 430.250. This is the starting point for determining the conductor size. Secondly, correct for ambient temperature. Since the ambient temperature is 40 degrees Celsius, you have to apply a correction factor from Table 310.16. This reduces the allowable ampacity of the conductor. Thirdly, adjust for the number of conductors in a raceway. Because there are 6 current carrying conductors in the same conduit, you must apply a directing factor from Table 310.15 cone. This further reduces the allowable ampacity. Fourthly, determine the minimum wire size. Based on the adjusted ampacity, select the wire size from Table 310.16 that can safely carry the current. This wire size must be rated for at least the calculated ampacity after all adjustments. As for the warehouse service demand calculation, the first step is to calculate the receptacle load. Multiply the number of receptacles by 180 volt-amps per receptacle. Secondly, determine the lighting load. In this case, it is given as 10,000 volt-amps. Thirdly, calculate the total load by adding the receptacle load and the lighting load. Fourthly, apply demand factors. Since this is a non-dwelling unit, demand factors can be applied to reduce the overall service demand. This typically involves multiplying the largest load by 0.8 and the remaining loads by 0.6, and then summing the results. Finally, these calculations ensure that the electrical system is safe and efficient, preventing overheating, voltage drops, and other potential problems. It is important to adhere to the NEC and local codes to ensure compliance and safety. This approach provides a detailed, step-by-step method for accurately calculating conductor sizes and service demand. It is crucial for safe and efficient electrical installations. The formula to calculate the adjusted ampacity of a conductor, accounting for both temperature and the number of conductors, is as follows: adjusted ampacity equals full load current multiplied by temperature correction factor multiplied by dirting factor for number of conductors. In this formula, the full load current is obtained from NEC table 430.250. The temperature correction factor is obtained from NEC table 310.16, and the dirting factor for the number of conductors is obtained from NEC table 310.15 current. To determine the wire size, you consult NEC table 310.16, selecting a conductor with an ampacity greater than or equal to the adjusted ampacity calculated in the previous step. Please note that the wire size must be selected based on the ampacity before any dirting for the number of conductors in a raceway. The dirting is applied after the initial wire size selection to ensure that the conductor can safely carry the required current under the given conditions. The purpose of the ambient temperature correction is to ensure that the conductor's insulation does not degrade prematurely due to excessive heat. Conductors have a maximum operating temperature, and when the ambient temperature is high, the conductor's ability to dissipate heat is reduced. The correction factor reduces the allowable ampacity of the conductor to compensate for this effect. The dirting for the number of conductors in a raceway is necessary because when multiple conductors are bundled together, they generate more heat than they would individually. This is because the heat from each conductor is trapped by the other conductors, reducing the overall heat dissipation capacity. The dirting factor reduces the allowable ampacity of each conductor to prevent overheating. In the warehouse service demand calculation, demand factors are applied to account for the fact that not all loads are likely to be operating at their maximum capacity simultaneously. This allows for a more efficient sizing of the service conductors, reducing the overall cost of the electrical installation. The specific demand factors used can vary depending on the type of loads and the occupancy of the building. The NEC provides guidelines for selecting appropriate demand factors in different situations. The reason that the lighting load is considered the largest load when calculating demand factors is simply because it is specified as such in the problem. However, it is possible that a receptacle load could be larger if the problem provided more information, such as the number of receptacles and their assumed loads. In such a case, the receptacle load would be considered the largest load when applying demand factors. These calculations are crucial for ensuring the safety and reliability of electrical systems. Overloaded conductors can overheat, leading to insulation breakdown, short circuits, and fires. Properly sized service conductors can prevent voltage drops, which can cause equipment to malfunction. Following the NEC and local codes is essential for ensuring that electrical installations are safe and code compliant. These guidelines are developed to protect people and property from electrical hazards. The calculations must be done accurately and thoroughly. Ignoring or misinterpreting these rules can have serious consequences.